What if I told you that running your CNC machine too slow can ruin your part just as badly as running it too fast? Most beginners think lower RPM is equal to safer cut is equal to better finish. But in reality, low RPM can quietly destroy your surface quality, tool life, and even your accuracy. So today, we are going to test it, break it down, and uncover what really happens when RPM is too low. Left pointing magnifying glass the setup, build curiosity. Imagine this, same material, mild steel. Same tool, carbide end mill. Same feed rate. Same depth of cut. Only one thing changes, RPM is reduced below optimal level. Sounds harmless, right? Let's see what actually happens, what RPM really does. RPM, revolutions per minute, controls cutting speed, how fast the tool engages the material. When RPM is correct, chips form cleanly. Heat is carried away properly. Surface becomes smooth. But when RPM is too low, everything changes. Polyscar's revolving light problem 1, poor surface finish. At low RPM, the cutter doesn't shear material cleanly. Instead, it starts rubbing instead of cutting. Leaves behind rough, torn surfaces. Creates visible tool marks and chutter lines. Your part may look crossmark dull, crossmark wavy, crossmark inconsistent. Instead of a mirror-like finish, you get something that looks unfinished and unprofessional. Fire problem 2, heat buildup. Here's something surprising, lower RPM doesn't always mean less heat. When RPM is too low, the tool rubs more. Friction increases. Heat builds up in the cutting zone. And because chips aren't forming properly, heat doesn't escape. Result, warning sign tool gets hotter. Warning sign material may harden, especially steel. Warning sign surface can discolor or burn. Hammer and wrench problem 3, tool wear increases. You might think slower RPM protects the tool, but actually, rubbing causes edge dulling. Increased friction leads to faster wear. Tool life decreases dramatically. Instead of sharp cutting edges, you get crossmark worn-out tools. Crossmark higher replacement cost. Crossmark more downtime. Chart with downward trend problem 4, chip formation issues. At correct RPM, chips are clean and well-formed. At low RPM, chips become thick and uneven. Sometimes they don't form properly at all. This leads to chip re-cutting, poor evacuation, surface scratches. Warning sign problem 5, increased cutting forces. Low RPM means the tool spends more time in contact with material. This causes higher cutting forces, more vibration, possible chutter, and that directly impacts crossmark dimensional accuracy, crossmark machine stability, crossmark tool life. When RPM is too low for the specific material and tool diameter, several technical failures occur simultaneously. 1. Built-up edge, BUE. At low speeds, the heat generated is insufficient to make the chip flow plastically. Instead, the high pressure causes small particles of the workpiece to weld themselves to the cutting edge. This built-up edge acts as a fake, blunt cutting tip, which eventually breaks off, taking pieces of your tool and your surface finish with it. 2. Tearing versus cutting. Metal needs to be sheared. At the correct RPM, the tool tip creates a clean shear plane. If the RPM is too low, the material isn't sheared, it is pushed and torn. This results in a fuzzy or matte surface finish rather than a reflective one. 3. Increased tool pressure. Lower RPM often leads to higher chip loads if the feed rate isn't adjusted proportionally. This creates massive radial pressure, which can cause the part or the tool to deflect, chutter. 4. Brittle fracturing. For carbide tools, which thrive on heat and speed, running too slow can cause microchipping. Without the proper speed to facilitate chip evacuation, chips can get recut, shattering the brittle carbide edge. The sweet spot discovery. Did you know that increasing your RPM by just 15 to 20% can sometimes increase your tool life? It sounds counterintuitive, but by reaching the proper shaping temperature, the material flows across the insert with less friction. The surface finish test isn't just about looking for shine, it's about measuring the roughness average, RA. If you run a test strip at 300 RPM versus 800 RPM on aluminum, the difference isn't just visual, it's a difference in the dimensional accuracy of the part. Choosing the right RPM isn't just about following a chart, it's about the physics of the cut. When the spindle speed drops below the optimal range, the results are often visible and audible immediately. Here is a breakdown of what happens when RPM is too low, structured for a deep dive into machining dynamics. You are running a fresh carbide insert on a piece of 4140 steel. You want to play it safe, so you dial the RPM back, thinking slower is safer. But instead of a clean, mirror-like finish, you hear a rhythmic thud and see a surface that looks more like a gravel road than precision engineering. In the world of CNC machining, safe speeds can often be more destructive than aggressive ones. Finding the floor of your spindle speed is just as critical as finding the ceiling. We've all been there, trying to preserve tool life by babying the machine. You see the surface finish turning dull. Or worse, you see tearing on the metal. You check your offsets and your coolant, but the culprit is invisible, it's the surface feet per minute, SFM. When the RPM is too low, the tool stops cutting and starts plowing, leading to a chain reaction of mechanical failures that frustrate even experienced operators. PM doesn't mean safe machining. It means inefficient cutting, poor finish, higher long-term cost. Sometimes, going slower actually makes things worse. Next time you are machining, don't just play safe with low RPM. Test it. Observe it. Optimize it. Because the difference between a rough part and a perfect finish is often just one setting, RPM. Speech balloon. If you found this helpful, drop a comment, RPM matters. Heavy Black Heart, like, share, and follow for more real CNC experiments and tips.